All right, everybody, welcome to Math with Grace. Today we're going to be going through Pre-Calculus Unit 9, Section 2, pages 32 through 39. We're starting today on page 32. We are going to have done Section 2 in 2 parts, so we'll be finishing Section 2 today, and it's really not much, as you could see from the page numbers, page 32 to 39, so this video shouldn't be too long. But we're starting today talking about combinations, okay? And so the first section here says permutations versus combinations. And so I'm just going to read through these illustrations, and then we're going to take a look at examples. To illustrate the differences between permutations and combinations, consider the letters A, B, C, and D, taken 2 at a time. We have 12 permutations. If order matters, we have 12 permutations, okay? But if the order doesn't matter, then we only have 6 combinations because AB is the same thing as BA. So technically, those only count as 1 when we're talking about combinations, okay? So remember, permutations, order matters. Combinations, the order doesn't matter. So another illustration can be seen by considering 3 students, okay? Mark, John, and Tom. If we want a debate team of 2 people, we have a combination, and the following shows how it can be divided, right? If you wanted a debate team of 2 people, order doesn't matter, okay? It doesn't matter which order you choose them, we just need 2, right? So there would be 3 possible teams. However, this is a combination, right? Order didn't matter. However, if we want a debate team with the second person being considered an alternate, then order becomes important because picking John first and then Mark is not the same as picking Mark and then John, right? Because Mark would be the head person and John would be the alternate. So we have 6 combinations there, or 6 permutations technically. So then they go into how the combination formula is derived. We're not going to bite into that apple. Let's just take a look at the formula. So it says, therefore, the combination of n things taken r at a time is equal to n factorial over r factorial times the quantity n minus r factorial. Okay? Now, we've looked at this formula before because it was posted earlier in the book, but here's where we're actually going to get to use it. So, taking a look at example 1, a track coach has a group of 7 men from which to pick a squad of 3 men to enter a current event. How many squads can be selected? The order doesn't matter here. You're not picking the most important first, right? It's just how many groups of 3 can be made from this 7 men. It's a combination of 7 things taken 3 at a time. And you set up the factorial like this. Now, your calculator most likely has a combination button, okay? Let me grab mine real quick and let's take a look here. So for combinations on my calculator, there is a little button right here, just right next to my permutation button, okay? The combination of n things taken r at a time. You can just plug it in and it will tell you what the answer is here. Let me grab the other calculator that I sometimes use, at least to show examples. Now, in this calculator, which is a Texas Instrument, what they use is this PRB button. And if you push it, then you can choose between a permutation or a combination, or that's also where the factorial button is under this PRB, okay? But let me go through the steps here so that you can see how exactly this problem is worked. So they have 35 squads, right? So we have 7 factorial over 3 factorial times 4 factorial. The 4 factorial is the one, since it's bigger, is the one I'm going to cancel. So it's going to end up being 7 times 6 times 5 over this 3 factorial, which is 3 times 2. 3 times 2, which is 6. Okay, my brain's going a little too fast. Okay, 3 times 2. Now, 3 times 2 is 6, so technically those can cancel out, which is 7 times 5, or 35 squats. Okay, so if you were just doing the math on paper, that's fine. You should come up with the same answer. If you're doing it on your calculator, of course, hopefully the answer is the same, right? However you choose to do it is totally fine. Next example. In a club with 10 members, in how many ways can a committee of 3 be selected? Part A. Part B is, in how many ways can the offices of the president, secretary, and treasurer be filled? Now, this is 2 different things. Part A is a combination. A committee of 3 has no order, okay? But Part B is a permutation because here the order matters. You're choosing a president, a secretary, and a treasurer, very specific things, okay? And that order matters because if you're filling the treasurer spot, you're not picking the presidential name, the person you've already chosen for president, right? It matters which order they're chosen in, whether they're going to be president, secretary, or treasurer. So then they've done it in both ways, right? It's in each time, it's 10 things taken 3 at a time. It's just part A is a combination. So there's 120 ways. And part B is a permutation. So you have 10 people to choose from, then you have 9 people to choose from, then you have 8 people to choose from, or 720 ways. Now they sneak in down here something I don't think they've mentioned yet, but it says by definition in the term 0 factorial is equal to 1. Okay, that's kind of important to remember because 0 factorial is not 0, it is equal to 1. All right, let's take a look at example 3. For example 3, it says, an assembler has at hand 15 transistors of a certain type. The equipment he is assembling requires 4 of these transistors. How many selections can he make without regard to order? Okay, combination, right? 15 things taken 4 at a time is 15 factorial over 4 factorial times 11 factorial. They've set it up here, right, where my 11 factorials cancel out. And then you have 4 over this. Now, they've stretched it all out, right? Personally, I would probably just reduce, right? 4 goes into 4 one time, and it goes into 12 3 times, and then just multiply these numbers together at the top to get my answer, which is going to be 1,365. Okay? So that is us using the combination formula. All right, continuing. Adding combinations. The total number of combinations of n things means the total number of groups that can be formed from n things, taking the things 1 at a time, 2 at a time, 3 at a time, and so on, till you get to whatever number n is. And it is this formula. Now, the part that we need to consider most is this part right here. But it is the sum of n things where r begins at 1 all the way to n of n things taken r at a time, combination. So it's 2 to the n minus 1. So that's a lot going on there. Again, this last bit is really the part that we are in need of. So it says, in how many ways can 6 balls be drawn from a bag? Well, if you're thinking about the bag, right, there are 6 balls in this bag. The order doesn't matter. To draw one bag, I have 6 choices. Okay, so I kind of did the math in the combination way. Okay, to draw one ball, I have 6 choices, right, because there's 6 different balls. Then you are drawing 2 balls at a time, so it's a combination of 6 things taken 2 at a time, which is a total of 15. Then the combination of 6 things taken 3 at a time, which there are 20. And the combination of 6 things taken 4 at a time, of which there are 15. The combination of 6 things taken 5 at a time, of which we're back to 6, okay? And then the combination of 6 things taken 6 at a time. Anytime you have a combination of n things taken n at a time, the answer is always 1, okay? As you can see here, it is going to be 6 factorial over 6 factorial, which is just a 1. Now, adding these all up, we get 63, okay? Now, looking at the formula, the shortcut formula here, it tells us it's 2 to the n minus 1, where n is equal to 6. So 2 to the 6th power is 64 minus 1 is 63. So this is quite a bit easier than the setup that I did, right? But I wanted to show you the steps that they come to the same answer, right? So example 2, if you have a bag with 8 marbles, how many different ways can those marbles be drawn from the bag? Okay, exact same problem, right? I'm not going to write out the 8 one because I did the 6 one because it was less numbers, right? But it's basically 2 to the 8th power minus 1. 2 to the 8th power is 256 minus 1. Now, as a quick review, although I'm sure this is kind of silly at this point, on my calculator, I have this x to the square button, like an empty square. That is how I get 2 to the 6th power, or I guess this was 8th power. So let me, 2 to the 8th power, right? Make sure you close your parentheses, and that equals 256, okay? Let me grab that Texas Instrument. I feel like one's a little bit different. So on the Texas Instrument, it's actually this little, I call it a caret. I'm not really sure if that's its actual term or not, but it's 2 to the little caret, okay? 8 is going to be equal to 256, right? So on a Texas Instrument, it's this little caret button. On my calculator my Casio that I normally use, it is this x to this like empty box, okay? But as you can see, it still has the little caret. Maybe you can see it. It still shows the little caret in here, okay? All right, moving forward. So that is how you figure out what these numbers to a power is, right? And some of these are kind of big. Okay, let's turn the page. So we are on page 34 doing some of these problems together, and we're going to start with problem number 44. Find the value of the combination of 7 things taken 2 at a time. Okay, remember, combination of n things taken r at a time is n factorial over r factorial times n minus r factorial. Okay, so the combination of 7 things taken 2 at a time is going to be 7 factorial over 2 factorial times 7 minus 2, the quantity factorial, right? Or 7 factorial over 2, because 2 factorial is just 2 times 1, times 5 factorial. Now, the 5 factorial I'm going to cancel here, so I'm left with a 7 times a 6 divided by 2. Okay, that's how I cancel out my 5 factorial. 7 times 6 is 42. 42 divided by 2 is 21. Letter A. All right, next one, find the value of the combination of 5 things taken 5 at a time. I already told you that the combination of n things taken n at a time is 1. I'm going to write it out in this formula way so you can see exactly how that is represented. It's going to be 5 factorial over 5 factorial times 5 minus 5, the quantity factorial, or 5 factorial over 5 factorial times 1, because this is 0 factorial, which is 1. And then this is 1, so the answer is 1. Okay. One more on this page, and we'll do some over here. Find the value of the combination of 13 things taken 5 at a time. So the combination of 13 things taken 5 at a time is 13 factorial over 5 factorial times the quantity 13 minus 5 factorial, which is 13 factorial over 5 factorial. And I'm really working this out the long way, so you guys can see exactly what's happening. And then this is 8 factorial. So 8 is the bigger one, so that's what I'm going to cancel. And I have then 13 times 12 times 11 times 10 times 9 over 5 times 4 times 3 times 2 times 1, which I'm not really concerned about, okay? Now, 5 times 2 is 10, so I'm going to cancel those out. 4 times 3 is 12, so I can cancel that one out. And I end up with 13 times 11 times 9, which is 1,287. Now, I'm going to show you how to put that one, which is letter A, by the way. I'm going to show you how to put that on your calculator in case you've never used your your buttons here before and you want to try them, right? So if I hit shift, so first I got to put my thing in. So I'm going to put my n in first, which in this case was 13. And then I'm going to push my n, my combination of n things taken r at a time. And my r, I forget, was 5. So on my calculator, it says 13C5. And I just hit equals, and it's 1,287. Okay? Just for fairness, I guess, or whatever you want to consider it, I'll do it here too. Oops. Clear, clear. So first thing we're going to put in is our 13. Okay? Then we're going to hit our PRB button, choose our combination, hit enter, and then put in 5. So I have 13 NCR5, and I hit enter, and I get 1,287. Okay, so that's how you use it on here. This Texas Instrument. If you have a different kind of calculator, you're going to have to look it up, because obviously I can't, I don't own all of them. I own a lot, but not all of them. Okay, let's take a look at problem number 52. Find the value of the combination. How many straight lines can be drawn through 20 points, of which no 3 lie on any one straight line? Okay, if 3 of them don't lie in any straight line, then we need 2. We need 2 points to make a straight line anyway. That's geometry, right? So we are taking the combination of 20 things taken 2 at a time. So that gives me 20 factorial over 2 factorial times 20 minus 2 factorial. I feel like as you take larger numbers, but less at a time, the number is not as big as you think it's going to be, right? Because this is 20 factorial over 2 factorial times 18 factorial, which is going to give me 20 times 19, right? Divided by 2. So really not as big as it seems. I'm going to reduce this to 10, and it's only 190 combinations, all right? Because we're taking many things a little at a time. It's really not as many combinations as you would think. Find the value of the combination for number 53. In Maricopa County, 5 persons are to be elected to the Board of Supervisors. If 8 persons are candidates, how many different arrangements are possible? So it's the combination of 8 persons taken 5 at a time, right? The order doesn't matter here. So I have 8 factorial over 5 factorial times 8 minus 5 factorial, or 8 factorial over 5 factorial times 3 factorial. Now 5 is the larger one, so that's where I'm going to cancel, and that leaves me with 8 times 7 times 6 over basically 3 times 2 times 1, right? But 1 is whatever. 3 times 2 is 6, so those cancel. And then I'm just left with 8 times 7, which is 56 combinations. All right, let's do one more of these together. Find the value of the combination. Number 54, a farmer buys 3 cows, 2 pigs, and 10 sheep from a seller who has 7 cows, 4 pigs, and 10 sheep. How many choices of animal does he have? Okay, so he's buying 3 cows, 2 pigs, 10 sheep. Okay. The combination here of our cows is there are 7 available. He's taking 3 at a time. This is cow. I don't want to get them mixed up. The combination of pigs, the combination of pigs is 4 pigs taken 2 at a time. And the combination of sheep is 10 taken 10 at a time. We already know that that one's a 1, right? He wants 10. The guy has 10. He's taken all of them. He gets 1. But let's figure out the rest of these, okay? So this is going to be 7 factorial over 3 factorial times 7 minus 3 factorial, or 7 factorial over 3 factorial times 4 factorial, okay? Canceling out the 4 factorial leaves me with 7 times 6 times 5 over 3 times 2, which is 6, so we're going to cancel that. I have 35 choices of cow. Okay, For the pig, I'm going to have 4 factorial over 2 factorial times 4 minus 2 quantity factorial, or 4 factorial over 2 factorial times 2 factorial. Now, canceling out one of the 2 factorials gives me 4 times 3 over 2. I'm going to reduce here, and so I end up with 6 choices. And this is a 1. So now it's 35 times 6 times 1. Okay? I feel like it's going to be 210. I always forget to turn that on. So 35 times 6 is 210. There are 210 combinations of animals that he can purchase. Okay? All right. Go ahead and finish the rest of these on your own and meet me back here for the final part of section 2. This final part of section 2 begins on page 36, and it is titled Binomial Theorem. Now, I don't normally read all of this stuff up here at the top, or any of it for that matter, but I'm going to today. It says the binomial theorem is a series represented by the quantity of a plus b taken to the n power, where that equals the sum from 0 to n of n over k times a to the n minus k b k to the k power. So the binomial theorem can be used to expand binomials raised to a positive integer of n when a and b are any number. Notice the formula used to calculate the combination n over k is included in the binomial theorem. Okay, we've been working with this. Instead of r, though, they're using the letter k this time. Let's look at now what that means practically for this lesson. It's kind of a shortcut of the combination formula. So it says Pascal's triangle is a triangular array of numbers where each number is the sum of 2 numbers directly above it. If you've never seen Pascal's triangle, I'm going to go through it briefly. We always start with row 0 at the top and then count down. And row 0 is always 1. Row 1 then is nothing plus 1, so it's 1, and then 1 plus nothing, which is 1. Okay? As we move down, right, the outsides are always going to be 1, but the middle is going to change because now I have 1 plus 1, which is 2. So I have 1, 2, 1. Then I have a 1, and 1 plus 2 is 3. 2 plus 1 is 3, and then I have a 1. Okay? Then I have a 1 again to start the next row, but I have 1 plus 3, which is 4, and 3 plus 3, which is 6, and 3 plus 1, which is 4, and then a 1. Right? See the pattern here? Then I have a 1, and 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then 1. Right? And this continues on and on forever, amen. Right? They've given us 7 rows here, but it does go on and on forever. Notice that the first row in Pascal's triangle is row 0. Also notice that each row begins and ends with a 1. Each row has 1 or more number than the previous row. Okay? These are all 1s. These are all going to be 1s. This is row 0, and this number is kind of in the 0 place. So for row 5, this is the 0 place, the 1 place, the 2nd place, the 3rd place, the 4th place, the 5th place. Okay? At reading those across, starting with 0, you should get the same as the row number. So the row 6, right? This is 0, 1, 2, 3, 4, 5, 6 things. Okay, technically 7, right? But we start counting at 0. That's just how it works. All right? So let's take a look at what this represents. So they want you to expand the binomial x plus 3, the quantity raised to the 4th power. To do that, you would go to row 4, okay, which is 1, 4, 6, 4, 1. Now, you'd have to have the Pascal triangle on hand, or you'd have to be able to, start it off and write it out yourself. And I'm going to do that for you in a little bit, just so you can see exactly how it's pretty easy. But that row is 1, 4, 6, 4, 1. Because neither of these numbers, well, this x value doesn't have a coefficient, it makes it kind of easy to set up. But it's going to be 1 times x to the 4th times 3 to the 0 power, because this is how the Pascal's triangle works here. The first coefficient, or the first variable or term, however you want to consider it, gets all of the exponent. So therefore, there's none left for this 3. In the next one, which is 4 times the group, right, we take this one down a notch. So here it was x to the 4th, now it's x to the 3rd, but I still have one exponent left, right? Or my exponent is supposed to be 4, and that goes with the 3. So now it's 3 to the 1 power. Then it's going to be x squared, 3 squared. Together, that equals 4. Then x to the 1st, 3 to the 3rd. Again, 1 plus 3 is 4. They always need to be the 4. And then I have x to the 0, 3 to the 4th. Okay, so you start heavy on the first term. They get all of the exponent points, I guess, if you want to think about that way. And then the first term loses one exponent point, which goes to the second term each time. So this is 1 less, 1 more, 1 less, 1 more, 1 less, 1 more, 1 less, 1 more, till it's balanced, okay? And then you end up with this value. And again, we will, well, actually, I don't know if they have, we will do some of these, yes, together. Okay. For example 2, expand the binomial, the quantity 2x minus y to the 3rd power. Okay, well, again, 3rd power means row 3, which is 1, 3, 3, 1. And that's what they have written here. So it's going to be 1 times 2x, which is my first term, and that gets the 3rd power. And then this negative, though, belongs to the y. We need to keep our signs, right? Negative y to the 0 power. Anything to the 0 power is just 1, so that's going to cancel. Plus 3 times x squared, right? We took 1 away, we gave it to the y. Then we have 3 times 2x to the 1 power. We took 1 away, we gave it over here. Okay? And then we have 1 times 2x to the 0 power, negative y to the 3rd power. Watch your signs. Remember, odd number of exponents is going to give me a negative number. Even number of exponents is going to give me a positive. Okay? So watch your signs there in case they try to trick you. Now, you might be wondering, what the heck does this have to do with combinations? Well, let's take a look. Remember, this combination formula was in, and I can't see it on my screen now, but I'm not going to move the book, was in the beginning formula for this binomial theorem. And it says binomial coefficients found in Pascal's triangle are the combinations of selected k objects from the set of n. Keep in mind that n is equal to the row beginning with 0, and k is a position in the row beginning with 0. Remember how I told you the position, we count across, we start with 0. So for example 3, trying to keep the triangle on the page here, or on the camera screen. Find the number of ways you can select 3 books from a set of 4. Now, this is simply the combination of 4 things taken 3 at a time. And if you're more comfortable just working out the formula, then go ahead and do that, right? But they're trying to show you kind of a shortcut way of looking at it, okay? If you have the Pascal's triangle, anyway. Our n is 4, so that is row 4, which is 1, 4, 6, 4, 1, which they have written here. Okay. Our 3 things at a time is the position of 3. So 0, 1, 2, 3 tells me there are 4 ways of selecting 3 books from 4 books. And if I'm going to work out the problem so you can see that it works out the same. So the combination of 4 things taken 3 at a time is 4 factorial over 3 factorial times 4 minus 3 factorial, right? Or 4 factorial over 3 factorial. This is just a 1 factorial, which is just 1. Now, that's just going to be 4, right? Because this 3 factorial cancels out the rest. And so it's the same answer, right? Either way you want to do it, whether you want to use, this is kind of a shortcut method, if you have a Pascal's triangle available, although you can Google it in an instant, have it available. but I'm going to show you when we do the work too how to actually write one up for yourself. Okay, example 4. Find the number of ways you can select 2 hats from a set of 5 hats, or the combination of 5 things taken 2 at a time. Okay, 5 represents what row we want, which is 1, 5, 10, 10, 5, 1. Okay, 1, 5, 10, 10, 5, 1. We want 2 things at a time, so we count 0, 1, 2, which they've done here, which is 10. So this is going to equal 10 without working out the math. Again, you could just put it in your calculator. They're just trying to show you a different way. Show you how the combination formula is also the binomial theorem, which is also this Pascal's triangle. Okay, they're all kind of related. Okay, all right, let's turn the page. Now we are on page 38, and before we start in this big area here, because number 65, in 2 or more complete sentences, analyze how to find the third term of the expansion. I would never ask anyone to do that. This is math class, not English class, right? But, I mean, if you are going on to be a mathematician or whatever, this is probably important. But I'm going to use this space to write out my Pascal's triangle. Now, again, remember, it always starts with a 1, okay? And then row 1 is just more ones, okay? But now we're going to start getting into the adding part. I have a 1 on the outside, but 1 plus 1 is 2, and then I have a 1 on the outside. I have my 1 on the outside. 1 plus 2 is 3. 2 plus 1 is 3, and I have a 1 on the outside. I start with a 1 on the outside. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and my 1 on the outside. Okay, the pattern is pretty basic. I have a 1 on the outside. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and my 1 on the outside. I have my 1 on the outside. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. 1 on the outside. I start with my 1 on the outside. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is also 35. 15 plus 6 is 21. 6 plus 1 is 7. And I have 1 on the outside. Okay, now, another pattern that's kind of unfolding. I guess, no, I don't want to, no, maybe that doesn't work. I just feel like I see a different pattern, but I don't know. I'd have to do quite a bit more. I am going to do one more row. The other page only goes to this row here, but I'm going to do one more. So I have a 1 on the outside. 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 and 35 is 70. 35 plus 21 is again 56. 21 plus 7 is 28. 7 plus 1 is 8, and my 1 on the outside. And again, it can go on and on and on. Forever amen, to whatever extent we need. But I feel like since the book page before only went to this row, that's as far as I'm going to go. I did one extra one just to show you. All right. Looking at the problems. Sally wants to expand the quantity 3a plus b to the 7th power. Which row of Pascal's triangle should she use? Well, remember, we count our rows starting at 0. So this is row 0, row 1, row 2, row 3, row 4, row 5, row 6, row 7, row 8. It's kind of identifiable by the number here, right? Row 2, row 3, row 4, row 5, row 6, row 7, row 8, right? It's just kind of how it works out. She is going to use row 7 because it is to the 7th power, which is letter C. For problem 61, what is the coefficient of the third term in a binomial that is raised to the 6th power? So the coefficient of the third term of a binomial raised to the 6th power. So row 6, 0, 1, 2, 3. Oh, third term. So I guess it would be 15, which is 1, 2, 3 terms. They're having us count it a little bit different. So First term, second term, third term is going to be 15, which is letter D. If we were doing our combination things, that's when we count starting with 0 and position 0, okay? But I guess if we're talking terms, it's a little bit different. 1, 2, 3, 4, 5, 6, 7 terms altogether. 62. Which of the following is correct expansion of 3x minus y squared? Now, a square is pretty simple. I don't know that you need to use Pascal's triangle, right? It's square, double square when we're talking about squaring something. So we would square the first term, which is 9x squared, multiply the two together, which would give me a negative 3xy, and then double it, so a negative 6xy, and then square the second term, which is a positive y squared. So that is letter C. Okay, Pascal's triangle is not necessary in that particular case. So I guess we're not really doing a huge expansion. Coefficient. Let's take a look at these problems over here. Try to keep my triangle on the page. All right, which row of Pascal's triangle should be used when looking for the number of ways 15 students can be selected from a class of 32? So it's a combination of 32 things taken 15 at a time. The 32 is what tells us what row. So that's letter D. How many ways can 2 flowers be chosen from a set of 5? So a combination of 5 things taken 2 at a time. So we're going to look at row 5, and we're going to look at position 2. Remember, 0, 1, 2, so the answer is 10. Right, 0, 1, 2. I know mine's kind of not really straight. Sorry about that. But that's how we do it. We could do the math too, right? 5 things taken 2 at a time is going to give me 5 factorial over 2 times, because remember, 2 factorial is just 2, times 3 factorial, or 5 times 4 divided by 2, or 10. Okay, so it all works out the same. I guess they're not diving too deep here into the work as they did in the examples, but I'm going to let you go ahead and finish the rest of this on your own. That's it for section 2. We will complete section 3 and finish this book next week. If you have any questions, don't hesitate to contact me. Otherwise, until next time.